Hello, thanks for the warm welcome. Let me just see, I need to get my clicker on. All right, oh, it's on this side. Thanks for coming. I'm going to tell you how to build a machine learning application in the browser, and I hope you'll be ready to start and hack. And if you do something, let me know on Twitter or per email or on GitHub, because I'm always very interested in what other people come up with. Some great ideas I've already seen. So, quick things about me. Oh, wait. No. All right. This is me on a good day. This is just a reference because I want to tell you that this is not me. I don't know if you know that there's a company, a Taiwanese company that builds computer towers. And they build like these amazing kind of like tables and like locomotives and stuff. And every time someone discovers on the internet that this company exists, they do stuff like this. They post it on my Facebook wall and are like, oh, look, there's like this. Did you know about this? And this particular friend of mine, he was so happy about it that after he posted this to my wall, he liked his own post and then commented on his own post with a smiley face. So yeah, there's like people just get so excited about it. Or another instance where in my new company, people discovered this, posted it, mentioned me, and then they're like, is that our Lian Li? I'm like, this is a company. Clearly, this is not me. And then someone discovered that there's a website, and they're always like, did you know about this? And well, I've been working in this industry for almost 10 years. Also, I've been on this planet for 30 years, so yes, I've Googled my name, and I've come up with this like 20 years ago, so thank you. In any case, if you want to follow me, the person, you can do that on Twitter, on GitHub, on Mastodon. I'm Chimney42 on the internet. And off the internet, I'm a software engineer at a company called Container Solutions. We're based in Amsterdam, although we have other offices in London and in Berlin, and we're going to start one in Canada soon. And during the night, I'm a machine learning, what I call myself, machine learning enthusiast. So I do get to do some machine learning at work, but the stuff that I'm going to show you and most of the machine learning stuff I do is actually my hobby, so I don't really have a life. So that's just about me. Let's talk about the more interesting thing. Let's talk about machine learning. So I guess most of you have already heard that there's this thing that's called machine learning. And maybe some of you already kind of know what it means, how it's going to change our way of thinking, of approaching problems. I just want to give you like a small, like short overview, basically. So we have expert systems, which are the systems that we're building now. Those systems are experts in the problems they want to solve. So for expert system, usually, what we have to provide as developers are inputs and the rules, what to do with that input. And then that expert system will give us the output. Now, in machine learning, as developers or machine learning engineers, or however you want to call it, we need to provide inputs and we need to provide the outputs. And what we get from that machine learning algorithm or thing, that are the rules. So that is like the major shift in how we approach a problem and how we think about a problem. So our focus basically is on input and output, or for a better word for that would be our data. So machine learning, right. The way that machine learning actually learns is quite similar to how we as people learn, or how every living organism learns. One thing that's very important is the experience. So experience in this case would be like the number of data points. So if you have a lot of different data points, you have a lot of like experience, different experience, broad experience. And then the other thing we need is repetition, which would mean like the number of training iterations. So over a broad, hopefully broad set of data points, we iterate a lot, so we repeat learning on those data points a lot, and this is how we slowly get to learn this particular pattern. Now, this is machine learning in general, so I'm going to tell you about machine learning in the browser, which is client-side machine learning, which brings a lot of, what's the word? A lot of good stuff, advantages, right. Advantages, like speed. So if you're, I don't know, in Germany, for example, the internet connection is not always that great. So when you have client-side machine learning, there's a big advantage that you don't have to wait for the server to answer. You can do your predictions on your client. So you'll get your predictions faster, hopefully. The other thing is availability. So similar to speed, there's also sometimes the issue that you don't have an internet connection right now. So you still want to use your stuff, your machine learning algorithm. And when it's on the client side, you will have it available all the time. And then lastly, big issue is security. So if you have very sensitive data that should not leave your client. I don't know what that could be, but there's this machine learning thing on iPhones where it sorts your naked pictures under a filter. So that ideally should not leave your phone. So that would be a good application for client-side machine learning. Right. In the abstract, I said that I want to give you some practical tools to start. So I need a practical example. And the example I chose is complementary colors. So for anyone who doesn't know what those are, they're basically the opposite color of any given color. So if you have red, the complementary color would be green. And if you have purple, the complementary color would be yellow. So the reason why I picked it is because Deep Learn JS originally had that as an example, so I could just copy and paste it. But it's also quite easy to understand, and also you can mathematically calculate a complementary color from the RGB channel of the input color. So this way we can create a lot of data points without having to go through a lot of data mining, which is quite tedious. Right. Okay, so first I want to talk about a few words that I'm going to use, and just so we're on the same page, I want to go over them with you. So in conventional programming, we have input, a function where we feed the input in, and then we get an output. In machine learning, the inputs are called the features. So you have in, let's say, housing price predictions, which is a popular example. You could have inputs that are square feet, number of bathrooms, size of the yard, stuff like that. And each of those single inputs would be one single feature. These inputs or features are fed into a network. And the network can be considered one big function. It can also be considered as a network of single functions. So a network consists usually of nodes, and each of those nodes is a function in itself, and the network as a whole can also be considered as one big function. So if you feed your features into a network, you get something that's called a prediction. So each network will give you a specific prediction, and this is more or less mapping to what we already know from expert systems. The major difference is that now we have this prediction, but it's not quite ideal, and we have to kind of change it to match that ideal prediction that we want to have, which is, well, I call it the desired output. And in machine learning, we talk about the target. So this is where we want to go, and this is the target. So the features and the targets, those are the things that we need to provide. Those are the inputs and outputs I talked about before that we need to feed to our network to teach it stuff. So this is our data. Let's look at the code. How would we set up this data in coding terms? So we start off with importing the TensorFlow.js library. And then in this case, I'm generating data at any given size. And we have to initiate two arrays. So those arrays are separate. We have an array with features, and we have an array with targets. They're separate, and the only way they can be re-referenced, so we know which features belong to which targets, is by the index. So it's very important that you don't change up the order in the middle of it. So now we go through a loop, right? And so there are some helper functions that I hid for now. Basically, what you need to know is that what we receive back is an array with 3 elements. The elements are values ranging from 0 to 255, so those are our RGB channels. And then we compute the complementary color, which is also an array with 3 elements. And now when we have them, we push them to our arrays, to our feature and target arrays, but we normalize first. The reason why we normalize is we want our algorithm to understand that 255 is the biggest possible number. Otherwise, if we don't do that, we might run into the problem that our prediction will go over 255 and then it will skew our prediction and the way that our algorithm understands what it's trying to predict. So usually normalizing stuff is very important. Then we have to define the shape of our features and our targets. The shape is the notion of the dimensions of our feature and target arrays. So the first number is the rows, basically, and we have as many rows as we fed into the function, because that's how many data points we have. And the columns, if you so will, are the number of elements, the number of features that we have. So in this case, our feature shape and our target shape would be whatever size we gave, and then 3, because we have 3 elements in our array. And then we return some object, and we can reference features and targets later. Right, so I created this checklist for us so we know if we're on track and what we need to do. So first we have to create some data. That's what we just did. Then we have to create this network, right? The network that gives us the prediction. Then we need to do something or other, and then, profit. All right. So for the network, let's talk a little bit about TensorFlow.js. So TensorFlow.js, it's a library by Google, and it's based on the original TensorFlow that's written in Python. I don't know if you ever heard of TensorFlow with Python? Right, that's quite a lot. So TensorFlow, originally Python said that the nice thing about TensorFlow.js is that it runs in the browser, and it utilizes WebGL, so we can actually use our graphic cards for calculating all our predictions, which means that we can be much, much faster when we train our model, because we're able to do a lot of parallel calculations, and we don't have to do everything sequentially. Right. The other thing about TensorFlow.js is that it can only deal in neural networks. It cannot do anything, any other machine learning algorithms like support vector machines or maybe just like linear regression. So this is networks only. So yeah, a neural network. Neural network might have heard, I just said it, that it's a network of nodes. And the nodes are basically single circles. So here, each of those circles represents one node. And the whole layer, the whole thing, is called a tensor. And this is a tensor, this is a tensor, this is a tensor. That is also the input tensor, because this is where we get our inputs. In this case, we have 3 input nodes because we have 3 inputs. And here we only have 2 output nodes because I thought it would be pretty. Don't get confused by it. You can have 3 output nodes if you want to. You can have as many nodes as you want to. And these nodes then are connected. In this example, they are connected in a way that each node is connected to each node in the succeeding layer, like this. And it just continues from there and then to the last layer. This is just an example. It doesn't necessarily need to be this way. There are other ways of network architectures, but I'm not going to go into that because otherwise I'm going to be here tomorrow. Right, so let's look at a single node. So in this example, I'm basically zooming in on one node. And to the left, you see all the nodes of the preceding layer, and then to the right, all the nodes of the succeeding layer. So in this example, we have 3 nodes, then whatever amount of nodes in the middle, and then 3 nodes in the next layer. So what happens is these nodes give us our inputs. Those are 3 different values, x1, x2, and x3. And then we sum them up to get a new value, which we then pass on to the next nodes. So here we pass on the same value for each single node. Of course, there are other nodes in this layer that we're looking at now. So in this layer, there will be y1, y2, y3 for this node. So now you're thinking, if all we do is summing up the inputs, then all the nodes in this layer will output the exact same value. That doesn't really make any sense. That is where the magic of machine learning comes in. It's something that is called weights, and these weights basically determine how these inputs get summed up. I'm going to talk about this in the second to next slide or so. But what you need to know about the weights is that they're properties of the node, so they belong to the node, and we have one weight for each input. So each input gets their own weight. And thus, like I said, these weights are the heart of the model. These weights determine how the model looks like, what we are going to predict. I'm going to show you here in this example. This is an example for a dense layer. Dense layer just means that the node of the preceding layer connects to all the nodes of the succeeding layer. So, for example, like this. Here we have a dense layer, which is the one in the middle. And what happens in each node is that we calculate a value, y, which is x1 times the weight according the weight that belongs to it, and then we add x2 multiplied by the weight belonging to x2. Then we can have something that's called an activation function. We don't necessarily need one. Sometimes it makes sense because we don't want that particular value, but we want that value represented in some other way. And then after that, we want Mai to add a bias. The reason why we want Mai to add a bias is because if you have the weight and the inputs multiplied and added to each other, this might just not entirely match what we want to get. So there's this bias to it that will change the value at the end. Sometimes it makes sense to use a bias. Most of the time, it makes sense to use a bias. The bias also is some kind of weight, so it's also dynamically calculated. It can change. Right, so this is a bit like, this is the most complicated math bit of machine learning, actually, which I try to condense into 3 lines. But let's look at the code. Maybe it might become more clear what I'm getting at here. So to the left, I have the basically control code, and to the right, there's some helper methods that hopefully help you understand what's happening or how to implement it with TensorFlow.js. So first, we need to create a model. All that is calling a function on TensorFlow on the library that's called sequential, which means we have a model where we add layer sequences. So we add a layer, and then we add another layer, and the data runs through the model sequentially. Then to this model, we add a dense layer. In this case, the dense layer that we're adding has 3 units, so 3 nodes, which is because we have 3 inputs, the RGB channel. And we also have to specify an input dimension, which is also 3 because, like I said, those are those 3 inputs. So this represents our input tensor. And what happens in that magical function is just that we take the model, we literally just add this layer, and then pass that config that I described there just in. It's pretty easy, actually, now. And then we add some more dense layers. So here, I'm just picking random numbers, basically. So we go from 64, the next layer has 32 units, and the next layer has 16 units. And here we use a bias. It just works better with a bias. I tried it with bias, without bias. With bias, it works. Here, we don't have to specify input dimensions because TensorFlow is able to realize that the input dimensions for this layer is the output dimension of the previous layer. So you don't have to think about that much. And then we add a dense layer that is our output layer. So again, we need 3 units because our output is 3 units. We use a bias, bless you. And here, we need an activation function. And this activation function is a string constant that's called ReLU. ReLU is short for rectifier linear unit. What it does is that for every value that's smaller than 0, we get 0, and for every value that's bigger than 0, we get that value. So it just rectifies all the values that are smaller than 0, so we don't get a negative number at the end. Right, okay, this is our network. So going back to the checklist, we had our data, now we created a network. Now we're going to go to the interesting part. So, right, for profit, right, don't forget, profit is the goal in the end. So the interesting part, that is the training. And the training might sound complicated at first, but it's really not that complicated if you think about what we're doing here. So we're trying to get from the prediction, we have our data, we have our model, so we can already get a prediction. Now what we want to do is optimize the prediction, make that network, change it in a way that the prediction will get better. So basically, all we want to do is we find a metric that tells us how well our algorithm performs, then we change something, and then we check that metric again and see if it does better now or worse. And if it does better, we just keep doing the same thing. If it does worse, we just do something else. That simple. So how does it work? Okay, so I'm trying to visualize this because it's kind of mathsy and complex, but the basics are not that hard. In this graph, I have the x-axis, so I have a model here that only gets one input. It's just one feature, just because we can't see 5-dimensional graphs here. So here, in the y-axis, that is our output. That is what we predict. If I show you this graph, what it means is that if you have an x that is, if our input is 20, the target, so this is the reality, this is what we want to predict, the y, the output is also about 20. If we have like 120 as the x, the output should be around 100, I guess, or maybe 110. So let's say that we have this as a prediction. So this is what we want to get, this is what we actually get, and this is not the same, right? This is not the same line. So when we look at one individual data point, like for example, when x is 100, the difference between those two, between what we want and what we have, that is the cost or the loss. And the cost or loss function doesn't just give you the cost for one single point, it gives you the cost for each data point that we actually have. So in all our training data, that's the cost or loss. It's some representation. It's not necessarily just subtracting. It can be Euclidean distance. It can be whatever. It depends on your problem which cost or loss function will be the best. So this cost, that is our metric. That is how we define how well our algorithm performs. Now what we need to do is try to reduce this loss, try to make it as small as possible. And the way we do that is with math. So I'm trying to explain this with another graph. So in this graph, the x-axis is the weight, and the y-axis is the loss. So if I show you this curve, what this means is when our weight, so the weight is what we multiply our input with. When our weight is like, let's say 40, then the loss is at like 45. If our weight is at 60, it's at 25. If our weight is at around 100, it's like, let's say 5. So what we want to do is to get to that point. We want to change the weight so the loss is the smallest. And the way that we do that is we start at any given point. And what we do is calculate the derivative. The derivative, if you remember calculus from school maybe, it's the slope of this curve. And we can calculate the slope of any given point. So to the left, it might be a little bit steeper, and to the right, it might be less steep, ideally. So then now we know because we can only move in one dimension, we can only move to the left or to the right, we want to go where the slope is less steep, because that is where our minimum is. So basically all we do now is take our point and just move into the direction where the slope is less steep. So this is now a really, really big step. Now we're here. Here, same thing applies. We calculate the derivative again. And in this case, now we have to move to the left. So we move to the left. And so on, until we hopefully at some point get to the minimum. These steps get smaller as we approach the minimum, but they are also, when the first step is getting too big, it could happen that we move over here, and then we just go away. So the size of the step is actually pretty important. It's one of the most complex things to find out when you're actually developing an algorithm. But the code is actually not that hard. So all we have to do here when we set up the training is we have to define a learning rate, and the learning rate defines the step of that, the step that we take. So if you feel like we're not approaching the minimum, but we should be, we just have to maybe reduce the learning rate. If it just never goes to if the steps are just too small, then we have to maybe increase that learning rate. We have to find an optimizer. In this case, the TensorFlow gives you a lot of optimizers. This optimizer is the SGD, is the stochastic gradient descent, which is what I just showed you. There are others, which I'm not going to go into too deeply, but we can talk about them later. And then we call a function called compile on that model. And this is basically, OK, we're setting up the training now. And we have to pass the optimizer, and then we pass a loss function. In this case, we just pass the string that then defers to that loss function. In this case, we're using mean squared error. What that does is, so it takes the loss for each data point, and then it squares it, which means that really big losses get exaggerated, and really small losses are not that important. And then we take the mean out of all those losses. Right, so that's basically all. So we have our data, we have our network, we set up our training, and now all we have to do is run the whole thing. And now you're thinking, like, I still don't know what's happening. This is the way that I felt. I learned everything, and I still don't know what's happening. So I'm trying to visualize this, because we're visual people, right? So we have our network. That's how we start. We have our data. We take our data, we feed that into the network, we feed that into the input, and then we propagate all that data forward. It's called forward propagation, because from left to right, it's forward for us in the Western culture. So in the end, we get a prediction that is 3. Let's just say it's 3. Then we look into our data again and get the target. What was the thing that we wanted to predict? Oh, that's 2. So it's not quite the same. We have to calculate the cost now. In this case, I'm just using subtraction because it's easier. So our cost now is 1. We take that cost, we feed that to our optimizer. The optimizer knows everything about the network, and it takes that loss and then does something that's called backpropagation. So now we're propagating data back through the network, and it will change the weights in the way that I just explained to you by changing by going the steps, calculating the derivative, and then going to one direction. And it will just go through the whole entire network and change the weights just a little bit. Not exactly like this, but similar to this is what actually happens. In reality, we don't do it for each data point. We do it for a lot of them. We do it for a lot of data points. Batches are what they're called. And do forward propagation of all of them parallelly. That's why we need the parallel computation capabilities. And then out of all of them, we calculate a loss. And we only take the mean loss, feed that to the optimizer, and propagate back once. That's the most efficient way to do it. Right, so the code for that, again, is not as complicated as the theory behind it. So first we define the batch size. So the batch size are the numbers of data points that we do at the same time that we calculate parallelly. The epochs are how often you go through the entire data set. So if we have a data set with, let's say, 32 data points, 5 epochs, then that means in total, one training iteration, we will do the calculation on 32 times 5 data sets, data points. Right, so the function itself is called fit. So we just call model fit. We pass it the features, we pass it the targets, and then we pass it this configuration. That's it. It's an async function, so you have to wait until it's done, and then you get a history, which will provide you with some information how well your algorithm performed during the training. So in this case, I got the losses because I want to see the average loss, because the average loss should go down over training iterations. Right. So now you all know how it works. Now I'm gonna demo this. So I have a video prepared, but I'm going to try to do it live. I don't know if I'm allowed to, actually. Oh, yes. Wait, I have to find my mouse. Oh, wait. I know I can't find it. Oh, it's here. I found it. OK, so ideally, right, stop. OK. Stop. OK, forget about it. So what I want to show you is that the input color never changes, the target never changes. This is the color we want to predict. You've seen, hopefully, that we started with some ridiculous prediction, and it will slowly get better. It will slowly move towards the correct prediction until it gets to a point where, to us as humans, it's virtually unrecognizable. So this is live, right? This is just, I didn't prepare anything. This is how it actually works. Of course, this is a pretty simple example. So ideally, let's see, we can change, for example, if I change the number of epochs, then what we should see, it's much faster now, of course, but also you see that the steps, it takes much longer for it to get to the right area, basically, and most probably it won't be able to get into the same area that we had before, so it won't be that good. Maybe if we change the number of iterations, yeah. So I'm glad this worked. Huh. Great. Thank you. I have to find my mouse again. All right. This is the best live demo I've ever had. Great. OK, so links. So you can go to my GitHub. I'm going to put the slides up on my Twitter later. You can go to my GitHub. There's the repository. I just pushed it like half an hour before my talk. You can check it out for yourself. You can run it for yourself. You can see the code. I used like web worker magic because yay, browser. You can go to TensorFlow.js, and they have great examples that you can try out. There's this nice guide to deep learning, which just explains some of the math basics. And this is the thing that got me into machine learning. This is a course on Coursera by Andrew, who's a great teacher. You can learn everything about machine learning there. It's very mathy, though, so be prepared to cry a bit, because I cried a lot. Right, so, and then lastly, icons, right? Lastly, I just want to say real quick that we're hiring. If you're looking to move to one of those beautiful cities, Amsterdam, London, Zurich, Berlin, let me know, talk about it, and then hopefully we'll see each other there, or maybe later after the talk. Thank you.